All right. Well, I mean, I think we probably might get a few more coming in, but maybe for the interest of time, we don't want to take a
Yeah.
lot of time. I'd like to introduce you if you're ready.
Yeah.
Great. So it's a great pleasure to introduce my colleague, Professor Ming Luo, who I actually met a few weeks ago at the CPS
Yeah.
review meeting, and I was very impressed by his poster. And here he is. He's an assistant professor at the School of Mechanical and Materials Engineering. He's actually a chair, assistant professorship at Flaherty, assistant professor. He's been doing a lot of robotics work. He was actually a postdoc from 2018 to 2020 in the Department of Mechanical Engineering at Stanford University. He received his PhD in robotics engineering from Worcester Polytechnic Institute in 2017. He's been doing a lot of research related to robotics, including agricultural robotics. He's going to be talking about it today. Soft robotics, snake robots, origami robots, and haptics. And his funding has come from different sources: NSF, USDA, and NIFA, and the Washington Tree Fruit Research Commission. Also, his work has been featured at the Wall Street Journal, IEEE Explorers, and The Verge. So, with all that, we are very pleased to have you here. Thank you for coming via Zoom to give us a talk. We are very excited about it. The floor is
Right.
yours.
Right. Thank you, Dr. Sanfei, introductions. Hi, everyone. And again, so during the presentation, if any questions, you can put in chat or you can stop me. I can answer that. So the first things. So today's talk, because this is a CPS, I mean, related to the seminar. My background actually is a robotic, but I will order my presentation more focus on the cyber physical system. So as the title said, I'm working on the agriculture field, and where I will talk about more about that. What's the problem here? So let me go to the slides. So so I'm in Washington State University. Actually, it's a land grant university. So the location is in Pullman. So it means that it's not in Seattle. Actually, we are in the Eastern Washington side. So which is actually the boundary when the Idaho and Washington. So we are near the boundary here. So because we are land grant universities, so we do at a whole entire Washington state, we have multi-campus. So Pullman is the main campus here, and we also have the Tri-City campus in the central of Washington, and we also have a Vancouver campus. It's not from Canada. It's Vancouver, Washington, which is near the Oregon. So which is the western side of the Washington. So since the land grant university here, so we one stress of our school is basically is for agriculture. So Washington State actually is the largest apple and also including cherry producer. So you may have questions that I mean California, I know they have a lot of there is also a lot of cherry producer, and but Washington is also that. But usually the cherry now we have is in May, but after like in June and July, the cherry more folks come from Washington State. So we are focusing on, so my project is focusing Apple, which is located at the central of Washington. And one thing I want to ask you to pay attention, it is we have not talk about the general Apple structure. Is what that means. It's not a general Apple tree. So we have a lot of researchers that from the agriculture side, which is develop we call modern apple ultra yard, which you look at the picture here. So this is actually two-dimensional. So it means that the most of the apple the trees they actually grow in two-dimensional. It's not a normal apple tree here. So it's basically most of the apples is why we do that, the reason is because you really want to the apple grow as almost the same size and also very big. So they really want to have the sunshine. So that's why they train the tree as 2D. So if any branch come out, so they will just cut the branches. So it's 2D. So this is the things also really good for robotic side because we do the robotic picking here, harvesting here is basically you really don't want the branches and the leaves block the apple because that will bring a lot of problem of perceptions and also bring a lot of problem for the we call motion planning here. You really want to avoid the tree and approach the apples. That's what bring a lot of computation. So modern Apple Ultra ER3 is good for Apple. It's also good for the robot to approaching. So this is the first things. The second thing here, you do the Ultra ER doesn't did have a lot of labor shortage issues here. Let me give an example here. For example, if we do apple picking here, usually the begin at the November. They only have probably 20 days for picking window. So that means that you went to the ultra yard, you go to ultra yard, you can see the tree is a huge tree here, and it's really hard to hire enough person to the workers to pick all the apples. So generally that you will feel okay, when I go to the ultra yard at December, this should be finished the picking season, but you still see a lot of apple is waste on the tree here. So this is another issues here. This is labor shortage. So you make wondering, yes, the robot can do that. Yes, the robot can do that, and they already has been the problem has been in West, I would say probably 40 years old, and still, if you check on Google and search on that, they don't have any Apple harvesting company exist or can be proper. I mean, can be I would say profitable, and which means that it's still on the experiment stage. So they have a couple issues here. So first ones, I want to say that most grower actually they don't earn a lot because you know so they don't have enough, I mean, actual money to pay the robot to do the work. So the first thing, because when you look at it, they have called advanced farm or FF robotics. Each robot system like this is cost of more than $1 million, and they really cannot afford that. So the second things is basically it's kind of so they really wanted because peaking harvesting window is so short and they really want to do the fast. So the problem here, if you look at the human pickers here, they can grab the apple 1 second, two apples 1 second quickly. But when you do the robotic, you will see that they are really slow. And sometimes the problem come from the perceptions. You cannot really locate the apples, maybe, and also it's really hard to do the calculation and approaching apples. When you're approaching apples, you basically the robot may not grab grabbed apples. So the two things. One is the efficiency, and another one is the high cost that most grower cannot afford that. But it's also an urgent issue here because of the labor shortage. So the solution we proposed first things because we always talk to growers. So what do you the robot technology you really wanted? So the first one, they really wanted a high speed robot. Second thing, they really want the device cheap. The third thing, you really want the robot. What that means here can run 24 hours a day. And also that when you're raining or when the temperature really high here, even they have a smoke around especially Washington State, they always have a smoke here from the mountains come out. They really want the worker cannot go outside, so this is the apple will stay on the tree. And that things is basically one of universal solutions is we talk the slide shows is apple picking, but they have other options operations. For example, is pruning, pollination, flower thinning, right? So they really want to just use one robot to do everything. So the problem that okay, picking season is 20 days, right? So you use picking app robot, then stay probably 1 month, then you just put the robot in the garage. That's you cannot do anything here, right? So we really want the universal robot. So this is the survey we asked Grover what you really wanted. Okay, so this bring the questions. So um so we wrote the solution of this problem as a psychophysics systems. So this is some come out the solution here. So it's basically here. So first things, is we are looking for one problem of the robot is slow is because it's action. What that means here is basically the robot and your camera know the apple position, but it's really hard to figure out how to approach in the apples, especially when your apples they are growing each other like an apple cluster. They don't know which one we're picking first. They get confused. And also that sometimes they don't know the right trajectory to approach in apples. So what we do here, we basically introduce, for example, the current Apple robot, for example, is only can achieve to peaking, for example, 60%. So this is actually current state of arc. So they have 40% apples is left on the tree the robot cannot handle. So the reason can be the perception, the perception here, the camera cannot is missing the apples because of some light issues or some the leaves may block the apple a little bit, or maybe they hide another apple behind. That and also the action part is basically the robot just couldn't figure out the right path to approach an apple. So what we do here, first one we do is basically use human intelligence to calibrate the robot. So to human know how to pick the apples, we'll guide the robot to picking the apple. So when you human guide the robot to picking the apples, if they succeed, they will be treated as the ground truth data to put in the machine learning. So this is one approach. Another approach here is basically we build a simulated Apple Ultra Yard, and we will do laser scanning of the apple tree and somehow to reconstruct to the 3D Ultra Yard, and we put all the robot in a simulation and to run the machine learning to try it. So this is just two different ways to somehow to make the robot is become smarter, which is well to add more ground truth data, which the current robot, the algorithm doesn't work, it cannot work. So this is the whole big picture for the CPS here. Okay, so how we do that? So, you know, we talk about here is more like you may think about, oh, this is probably a software side because everything with calibration get the trajectory here, and we basically verify the trajectory and put the database to machine learning. It's more a software side of the project. Actually, it's not. So we basically to do is basically we are thinking about what's the best robot to on this project. So again, I mentioned here the current robot is so expensive and the current robot is kind of slow, right? So what kind of robot is be more faster response and also low cost and can be covered all the operations. And also I want to mention here is also let human easier to calibrate that. For example, I gave you the introduction. You've got a case that if you calibrate a 6 degree of freedom robot, so this is probably is kind of hard to map to the each joint or position because they have reverse kinematic problem here always. So first one, we talk about hardware. So this is the hardware here. I wanted to emphasize again the Apple Ultra Yard or modern Apple Ultra Yard here. So this is the 2D I would say not 2D, it's 2.5 dimensional apple trees. And most apples is not blocked by the branches and also leaves. So they do have some apple cluster if you look at the bottom picture on the right. So this is kind of difficult part to pick because you see the apples, but you really don't know which apple should go first. The problem if you pick up the wrong order and you pick one apple, the other apple will falling down the ground, right? So this is kind of waste. Okay, so this is for this is a second thing. So and is you are talk about it here is basically they bring a challenging for robotic side. It's not cyber physics system side. It's a robotic side because Apple can even this one doesn't have any branches and the leaves, but Apple is grow any directions, any positions. So unlike the industry settings, you really know what's the location of each, I mean, object you're grasping. So this is really hard actually from outdoor environment that your robot to figure out each path to locate to each apples, which is we basically call the motion planning problem that it's impossible. It's not a good idea to say that I will put a 6 degree freedom or 7 degree freedom robotic manipulator to the task because you know it will increase a lot of computation for the reverse kinematics. So, and another thing, assumptions here, that currently my collaborators, they did that very good machine vision problem here is basically they can detect the apples near the 99% in very short times. So the question is basically perception is not an issue here. The real issue is actually the action. So the action part that is called motion planning and control. That you see the apples, how we approach the apple as quick as possible, and also as it will increase the success rate. So so then we bring is basically my title talk about is a soft robot. So what a soft robot means here. So they have soft robot is made by the soft material. Compared to rigid robot, it will be have a certain benefit. For example, here it makes the human safety, so human and robot can working together. Or they have a flexible body, will not damage you. For example, if you have soft robot, will not damage the tree, will not damage the branches, will not damage other apples. So it's safe to contact, which is what makes all the computation for motion planning is much easier, right? Because the motion planning is basically to find a path to approaching the apple, also not damage any trees. So we propose a solutions is basically is called from my postdoc lab from Stanford. It's called soft growing robot. Is which is pneumatic robot and basically to pneumatic to it's kind of growing like a fabric and plastic and softer material. So the good things is a linear position, linear growing motions here. If you see the apples, right, the shorter distance is a line, right? So this robot actually doesn't have any joint, and you can see the apples just directly grow linearly to approaching the apples. Again, we only to use in the 2D 2.5 sorry 2.5D modern ultra yard because all the most apples they don't have any branches leaves block on the front. So the reason I want to say that my paper sometimes my paper get rejected because the reviewer think that they don't realize this is modern apple trees. They think about the regular trees that oh your robot how your robot avoid the branches. So they will bring this kind of questions that is out of scope of the our paper. So that's why we I wanted to emphasize what's the problem we are looking for here. And linear actuators and fast because it is a pneumatic driven. So if you build, they have some researchers to develop a linear actuator to picking apples use a rigid transmission. For example, you use linear screw, whatever here. But the problem here it is will slow down the speed because the linear screw that the gear transmission is really not the optimal one. So this one is you have pressure, you just grow and you can reach a target. So it's fabric body, everything is really kind of cheap, low cost. And we won't try to do because people are criticized for soft robot is basically, one is you're not because your material is not precise enough. Second one, it's not stiff enough. People may question, oh, you want to use this approach. Are you really sure the robot can carry the apple? So that's one. Okay, are you sure that robot can pick an apple that's precisely picking the apple and grab the apple? And also, reliability here, you are pneumatic and you probably sure here is just a plastic sheet. It's very easy to burst, right? If really you will be blew up somehow. So if a nail count, it will blow up. So how to improve the stability and the robustness? So the third one is the last one is again. So we want to try to robot to adapt to different operations. Can we have the one solutions of the robot here? So let me just talk about one example here. So we basically our lab to try the robot is basically so this is the structure for the safety here. We increase the pressure, we increase the pressure and to see what's the stiffness change that reach enough to carry an apple here. So this one the student is turned very high pressure is 18 psi. So it's kind of really rigid. So what is the solution we have? It is because the robot is soft. If we have very good fabrication here, to make to tolerate input inject enough air pressure to make it rigid. So it will be have stiffness, will be enough payload to carry apple, and because it's rigid being, so it's also kind of can to reduce the uncertain motions and also to improve the position to do the position control. And we basically this is some CAD designs. We have a robot that can do linear motions. The question how we steer the robot, we basically use a cable-driven approach, and we also have the N factors amount which can carry the gripper, can carry the cameras, can carry the scissors, can carry different tools, which can adapt to different operation. So again, we try to solve the problem here. We try to develop a low-cost, robust, and fast response robotic platform, and then which can carry any tool and use any machine vision technique to achieve different operations. So this is the one example here. Our robot here is basically this is show the workspace. It can grow. For example, I'm not sure how to convert to the inches, but it's kind of this 1.2 meters and can the maximum bending angle is 60 degrees. And you can see the robot can be much shorter. So that's about the workspace. And this is the video how we can grow and retract. So again, right? If you see the apples, and because the apple doesn't have any branches block you, right? So what's your solution here? So the robot the tendons will steering the robot to the right direction towards the apple, then grow linear grow with a short distance. It's a fast one, and the growing speed actually is not is really determined by the pressure. So, and also the internal pulley to release the material. Actually, they don't have like lead screws. It's the rigid gear mechanism solutions which have efficiency issues. And this is the current payload and the speed we are trying to do. So basically, we are not on the stage that we have enough payload to carry one apple and the camera gripper with no problem. And we also on the speed, and we can keep increase the speed. Now it's a 13 inches per second, but we can definitely have more pressures, and we can have the more faster releasing pulling here. And also our robot can tolerate 20 psi. It's actually really huge. And our lifetimes is basically we run the robot in the live in the lab. Every day is probably every day is only broken and half year. So you are talking why that true here? Because our robot, the fabric, you see the white one, is basically is very strong fabric and with TPU coated. So it's really like the features really like your jacket, rain jackets. So that's why we're very higher quality of the fabric. And this is another something here. Well, I want to talk quick about that, right? So we have a robot, and we want a robot to approaching apples, right? So then we'll bring the problem here: how to control the robot fast to reach the positions, right? How to develop the controller here. So we basically start from traditional modeling here. We get a kinetic model, and then we verify the model accuracy because you know you have the model you can predict, for example, I want to reach the apple, you can predict how many, what's the length of the robot, what the steering angle should be from the model. So you have a good initial guess. If you have initial guess, you really make your controller to adapt to converge to the desired target much faster without any, pre-knowledge. So this one, another one, because Our robot is the 4-degree freedom. You think about it, we're steering at the 2D surface. You have three steering the robot and then we're growing robot, and we really want the robot length and the two steering angle to convert at the same time. So that's why we use a modern reference adaptive control here. So the problem here, if the robot length is already reached the design target, if the two angles, not one of the angle not reach a target, they will screw up the other 2 parameter stability. So that's why we really want 3 parameters to reach the target at almost at the same time to avoid that happens. So this is all the control stuff, the structure. I'm gonna skip that. This is just we use model reference control here. You can see the 3 parameters can almost convert at the same time. Okay, so this is the robotic side here. Now we are talking about is machine vision side. So I'm the person to do the motion vision of my collaborators. I just mentioned here they have existing algorithm like a Euler or V7 object machine vision. They can detect 99% of apples. We also can have the not RGB also have the depth information. And the algorithm can detect which apple should be picked because it is very neutral or not, or what the location of the apple eye or the robot should be picked. And then we are also have the cameras, also have the grippers. So this is the gripper here, and the gripper here is we show that our robot payload 3 pounds, apple 1 pound, camera 0.5 pounds. So then we calculate that okay, the end effector must be less than 1.5 pounds. So what we do here, we still use a soft material called a soft gripper here. So it's basically it's the silicon rubber and with some TPU material here, everything the inside is as skeleton 3D printing that. So what we do here, this material is soft. So basically you grab the apple, you don't crush the apple. If you use a rigid apple, rigid robotic gripper, you may crush the apple, so you have to do some force control. These grippers can wrap around the apples with different weight and with different size, and it's kind of lightweight. And the question, how we detect the apple will be grasped. So if you look at the circle on the palm, so this is actually the limit switch. So when you grab the apples, when you limit switch trigger, the apple is make sure it's on the palms. So this is all the fabrications, and we try the gripper here, and then show that the gripper with a skeleton is what can approach 87% apple you can be picked. We tried in outer yard. Okay, so this is a demonstration we integrate together. So when you see the apple here, so the robot will grow and picking the apples, and then will be releasing the apple on the bin. So this is just rough. And so everything is automatically, and we already have the onboard cameras, and also, and we are ready to test this robot to commercial ultra yard in the this coming picking season. Okay, so this is a robot. So the robot, I just want to make the conclusion here is a low cost, and everything the cost is under $5,000 for R&D costs. So what we do here, if we really want to do the commercialized stage, what we do here, we have a mobile robot, and we can put a robot each side at least three robot containers. So basically, because our robot is cheap, and our robot is kind of easily to compute, very easy to do the computation. So we can deploy as many as possible to improve the efficiency. And our robot also another thing we back to CP as a proposal because our robot each location is only have one solutions. What that means here, if you pick up the 1 point XYZ, they only have one solution for robot length and the 2 steering angles. If you talk about like a 6-degree freedoms of a robot here, they have IKU, so same position, they may have a different configuration because it's joint. They make the redundancy here. So this one will make our calibration is much easier to mapping. So if we calibrate robot, we point out the location here, the robot can easily to solve the solution what the length and what's the angle it is, right? So it will improve the speed. So make a conclusion here. So what we do here is basically our robot is already ready, already finished in the lab testing. We'll bring the ultra yard in coming season to the in-field study. And we still want to improve the speed and payload and positions. And we also have, I don't show here, we already have the onboard cameras to locate at soft robots. So basically everything is onboard. And we also try to do is basically like the picture here, multi-robot solutions that to make sure that they can collaborate each other to achieve the very kind of much higher efficiency and the performance. Okay, so this is the robot side. Now we'll talk about the television side. So how we use human intelligence to teach the robot to, if the robot has a problem to approaching the apples. So the solution is use the VR device and plus machine learning. So what we do here is basically this is a it means that robot in ultra yard, the human operator is not in ultra yard. It should be different locations. So what we do here, so the robot have the cameras and to stream the data to the VR glass, all in the monitor. We still not decide which the right one. And you see the student here has a joystick, which has the sense the 6 degree freedom or 3 degree freedom of the pose. And what we try to do is basically we map the user on the pose to the robot to achieve the picking scenario here. And we also we also develop the haptics. So why we need the haptics? So for example, the haptics, if you don't know the haptics is means that if you wear, for example, Apple Watch will provide a vibration here. So here we use a software robot technology here to have the full punch models to basically you look at the picture here to simulate the vibration or do the normal indentation. So why is so important here? Because when you do the calibration here, everything information is from your eyes, right? The robot, you look at the ultra yard where the apple it is, and you try to get the robot, you try to make sure the robot at the right position because it's still the remote. So you may miss some information here. So for example, here, it's a robot out of workspace, right? It's keeping moving your arm, but robot already out of workspace, right? So then haptics can give you feedback to let you, oh, okay, your robot out of workspace, you have to go back. Another one we are thinking about how we regulate the human. So for example, some human is really it's really to shaking the hand sometimes, and we really want to guide the human to approaching to generate the trajectory much smoother. So this is we still on the investigation here whether we should add haptics in a whole the television stage. So this is one demonstration here. We still own the lab, right? So we basically, this one doesn't have any haptic device here. So we let the students just use VR. You can see they have the front cameras on the front at the robot, the manufacturer so that's only information you can see. So the student use the joystick and to match his position to picking apples, right? So the other something we are observe that sometimes the students are missing the apples because they have not enough the vision on the depth information. They may miss that they are not really sure the depth is the right. So we may think about maybe the haptics one can guide the robot, can guide the human calibrators to make sure that the robot the gripper to approaching apples to mimic the depth arrows here. So again, so just think about the scenario here is basically if the robot in ultra yard they couldn't pick the apples. So what we do here, the human will jump in and use calibration device to guide the robot to pick in the apple. The robot couldn't do. If the human can guide the robot can do it, so that trajectory will be recorded. and we'll do some smooth the trajectory here, and to put it in database and let the robot learn. Definitely, we'll also do some augmentation data for that means here, so we can rotate the apple position. For example, now 30 degrees, now we can do minus 30 degrees. So somehow to augmentation of the data. Why is it so important? Because we talk about robot for machine learning, the most difficult part is basically we don't have enough data, right? So for example, in this case, the student may need to spend kind of 1 minute to figure out the trajectory, the right trajectory approaching apples, right? So you think about that, even whole day, the how many trajectory you can generate, right? So we really want to write augmentation algorithm to make sure you expand the ground truth data to let it improve the robot act successful rate to target some difficult tasks. Okay. So this is the second part. Now I want to talk about a different things here, another aligned to this project, but it's not really like a CPS. It's basically we also propose another solution here. The repeat the difficulty here. So the current robot is kind of slow and it's not efficient because they only can pick 60% of apples. The problem here, environmental is unpredictable. Some apples is located very weird locations. The robot is difficult to approach. And also the identification here. So some apples we block by the leaves still happens, or maybe branches they cannot recognize, right? So they will waste a lot of time for machine vision here. And also the speed, that's a very some again, Apple locate some positions is really computationally to spend time to figure out the right orientation location to approach. So the questions, instead of to use all the technique to improve the success rate, can we to do is basically we do human robot interaction approach. So what this means here, you look at the picture here. So it's not the human will pick an apple first, then robot to pick. It's not the robot pick first and human then pick. It's basically human robot will working together. So I'll give you example here. Here basically, all right. So human doesn't want to bend the knees or climb the ladders to pick an apple. So this one robot can do it. And sometimes you see the apple clusters, which one the robot is very difficult to pick at the right order, or they can just fail. The human, no, the robot couldn't do it. The human will do first. So this is something that the human and robot they will learn each other to make a successful rate. It doesn't mean the robot and the human they will talk to each other. They will learn each behavior to convert a point that they are really feel comfortable. Okay, this is our future research directions. And one thing I want to ask your attention here is our robot made by the fabric. So it's totally safe for human robot interaction, even is a physical interaction here. So like this picture, so the robot can contact human body without any damage, without any safety issues here. So this research, we really wanted to ask is psychology issues. It's basically, do you really want the robot to work with you as close as possible, right? So the current if you look at the current standard, is called ISO industry robot standard here. The human robot need to keep 20 inches distance. What that means here, if you close the robot under 20 inches, the robot must stop. So there's a question here. Okay, the technology is maybe ready in the future if we have soft robot. It's basically totally soft that when do the human robot in action. I will show the video. So if that stage will come, for example, like a caregiver, so this nursing and something that you really want a robot working together as a physical contact, what would you do? Right? So we want looking ahead for psychology here. Is really want to see the robot is affect your psychology. So just like there's someone really against that new technology here, right? So feel anxiety, or they may take our job, or really don't want this robot. So sorry, something like that. So what we do here Um, so this is a true robot here. So on the left side is soft robot, right? And right side is rigid robot. So the question I'm asking you that in the future, right, you may have a, really want to buy a robot to clean your kitchens, or maybe just like a third, we call the concept is third hand, right? You really want an additional hand to help you, right? So do you really prefer the right robot or left robot? Because I can tell you the left robot is have uh, much better safety features. And again, soft robot compared to the rigid robot, it still have a problem for the perception payload, right? So we are working on is basically we are built the same scale of robot can do some useful tasks, can grasping something and can deliver something. That's what we do. So this robot can save. I both show the video here. I let the robot crash my face. It's fine, and it's pixelized just like an airbag, and will be because soft features and observe the contact force. And this is another robot will show that this is the instead of the linear line, this robot can go also grow and retract and so also can curve. So think about that when you're a robot, the robot can across your body, curve your body to approach something here, right? So this is the technology we're working on. Okay, so let's back to psychology. So there's a question here. So if you talk about robot, if you talk to a robot working with you, couple of things you may be pay attention. One is soft and rigid. The material, appearance, maybe male or female. But another thing, more technical part side is basically what the distance. Do you really want what's the distance proximity you feel uncomfortable you feel comfortable to work with? The second thing, the speed. Do you really prefer a speed the slow robot, or you really prefer the robot go very crazy aggressive? So this is the things we try to find an answer here. And so this is a scenario. I work with our school psychologist with Tahuya Probus, and she's a social psychologist, and she did a lot of research on the fear, anxiety, lost job in security stuff. So she has the technique, I would say the measurement to quantify the human anxiety. So what we do here, we do some tasks here. So basically we do, uh, it's called collaborative or collaborative task. Cooperative. So it means that, okay, you develop, you put, you send the cube to human, you send to to put the tube in a box first, let human grasp, or you basically to give the tube to human directly, right? You give the cube to human directly, it means they are really close to interaction, right? If you put the cube in a box, then stay away, then human to grab the block, right? So this is they keep some distance. So the second thing is we basically try the different speed of robot. We run the robot fast or run the robot speed, and then we record a video because that's the first stage, and we don't do let the user participant to come to lab to do it because that's kind of a lot of RB issues. So what we do here, we just record a video, ask the human opinion here. So we basically test 122 students here. So this is the result. The result is if the student who has played with a robot before or play a lot of computer games, they prefer the robot go faster. If they don't have any experience, they prefer the robot go slower. Another ones in these studies, they show the proximity is really not important and significant to affect the human psychologist. But I won't say this one because they only to look at the video. It's not, we feel that if we bring the participant into the lab and play with the robot directly, we feel the proximity may be affect a little bit. So we are not sure that we are not the second stage. We already are waiting, writing proposal. We almost get funded, but the agency get cut it, so we still wait what's going on. So this is another thing we try to do. So this is a reference here. I think that's all my talk. And first one, I will just thank for you attendance. And also thanks for my collaborators and my lab. I have one postdoc and Kai Yoshida. So he will be joining UCLA as assistant professor at the fourth semester. And also my PhD student. I also work to thanks for all the donors. I'm not donors, the funding agency, NSF, USDA, NIFA, and the Washington Tree Commission. And thank you. I'm happy to take any questions.
Thank you for such a fascinating talk. We have time for questions.
Yep. Thank you.
Well,
I have a question. When
Yeah.
the soft gripper fails to pick the apple, is that typically because of the way it approached or something wrong about how it tried to grab it, or is it that apple might just be like harder to pull off? Like is it a gripper problem or an apple problem?
Okay, let me back to yeah, you asked a good question here. So let me show this one, right? So you can see our robot can retract it directly. So when you grab the apple, you can retract it to attach detached branches. So our force is enough to detach apples. But the problem is the grower doesn't like that because they will damage all the branches. If you look at my if you have my you look at my if you can see it, so they really want human picking the apple to grab the apple, they are lifting a little bit. So it's that motions. So now we are doing that. I haven't shown in the slides. We have the gripper, which we add another twisting motion. So instead of retracting, we also do twisting to avoid the branches to tail up. So this is the one things. But so another thing I want to mention here, the grower told us they really don't like gripper idea. I can tell you, people are always do the grippers. The best way is use thesis to cut the stem. But the problem is not, I would say not bring to robotic problem. It will bring to the machine vision problem here to how to detect very tiny branches to cut it. Then there will be another problem here for the computer science major here. So that's I'm not sure that's the answer your question or not. Yeah.
Yeah, thank you. There was a question in the chat.
Okay. Incorporate heavy assume.
so do you want to read it or do you want me to read it?
Yeah, I can read. In collaborator human robot system, how do you ensure transparency in AI decision making, especially when machine learn from human behavior in real time? This may be essential for safety, legal, and privacy concern for considering all sensors and data collection. I imagine that transparency is also key for increased trust in automation and robotic systems. Yeah, so let me talk about this way for the technical part. I'm already is we are doing all the AI for the simulator, which is but still needed to verify in the let me see the still verify in the real ultra yard ultra yard. So the first things, so we believe to do decision making is true, but when you do actions, for what it means actions to let the robot to picking up to find the right path, we feel the AI for simulator may be not enough because the physical mode and the simulator, they do have a certain gap. It means that when your simulation working and in reality may still not working, we still need to try that in the Apple Ultra Yard. But for you talk about privacy or regulation here, yes, it is happens, but I don't have any very good answer for you for honesty about that. Okay, I hope that's gonna answer some questions. Yeah.
Thank you. Apparently, yes. Thanks, Kifo.
Yeah.
Other questions? Hey, do you have a question?
Hey, Tan.
Yeah, thanks for a great talk. And
Yeah.
I have a question about your end effector. I mean, not end effector. I mean the robot arm. And the first thing is you said you pressurized it pretty high, but
Mm,
so is it like you can pressurize more or less depending on which type of task you're doing? For example, maybe if you pressurize it too much and at your approaching phase, maybe it may have to, you know, damage the branch or maybe damage the crop. So maybe, yeah, that's one of my questions. And the second question is, well, it's more like some like high level question. So as this video shows, it's doing great, but it's definitely not like human speed, like
mm,
1 or 2
yeah.
clicks per second. So do you think if your robot system can achieve that level of rapid motion if you do something interesting adding on to your current system?
Yeah, 10. Good questions. So first one, I want to ask you a question. Do you know self-growing robot, right? The all the mechanism. You're
Yeah,
pretty
yeah,
sure of
yeah,
that because from Mike
yeah.
Lab. So
Yeah.
so first one, speed. We definitely can achieve that. So the reason we can do is now still prototype. Growing robot, when you're growing, two factors. One, the pressure flow rate is higher. Another one is the central pulley releasing the material, right? So if your pressure huge, but your central pulley releasing the material so slow, then the
Mhm,
robot will not fast. So I
mhm,
don't show here because the the central pulley, you see the container here, right?
mhm,
We actual center pulley is outside.
mhm,
So basically, what we try to do, we already purchased the very huge brushless model.
mhm.
It probably can turn around 60 amps.
Okay.
So, so what we do here, now the speed, you can see the slow speed here is not limited by the pressure, actually is limited by the central pulley speed.
I see.
So
Mhm,
again, so everything I want to tell you is everything can do tuning. We can tuning very good speed stuff. You are talk about okay. So if the speed is fast enough, will damage the branches. Yes. If the robot break, they were shooting quickly. They will damage branches. Yes. So then the question, then I would say if the robot not quick, right? So if we know the positions because we know the target and we can stop that and it will be fine. Again, the robot we are talking about is only half half meter long. It's not a really long one. So they really want just short distance. And it's everything is engineer. It's not a science that how we and again the robot body can tolerate 20 psi. It's really big. It's like just your car tire. So yeah.
mhm. Yeah, thank you.
Thank you. Any questions?
So you said that you're planning to test the system in
Mhm.
this coming harvest in the fall.
Yeah.
So are you also solving the problem of navigating the keys where the trees are? The terrain is typically not very friendly, right? It's sloped. It's probably full of debris and rocks. Are you looking into that problem of navigating within the lanes where the trees are planted?
Yeah, I'm looking for the robot self and all the uh, again, so we bring the Apple Ultra Yard is the tree is very training very well. It's only 2.5 and two dimensional. So first things, and we bring the robot to test things, and all the cameras we have my collaborators already have the cameras and the machine learning algorithm to make sure the most Apple can be read and we just do honestly I haven't really no answer. We just from beginning for this project we really want to just test the robot whether first one can pick an apple on the real ultra R tree. The second one if we can pick what's the successful rate, and what's the locations, some Apple posts that robot couldn't do it. So that's our goal here. Yeah.
Okay. I guess in your movies that you're showing us, it seems pretty successfully done, right? But between us, maybe we can stop the recording. But how many tries does it take to get this Apple pick right? Is it a simple task, or this is one attempt out of many? Can you tell us what's out there in terms of efficiency and success?
So let me tell you this way. So I show here is on a lab simulated environment. So you see the attached detached apples is basically used on magnet. So the quick answer is Apple Ultra. If you bring a robot to Ultra Yard, maybe the first testing we cannot grab any apple. So that's kind of hard. Is basically the lab simulated environment and real environment is so different, and we don't know. So that's why let me give you another example here. So if you so they have a journal called the Journal of the Field of Robotics, and another journal called IEEE Transaction on Field of Robotics. They basically say we have to do to bring the robot to Ultra Yard, not in lab simulate environment. So that's you can see the gap here. Maybe our robot can succeed to picking the apples, but I don't know. Even people use regular robot to picking the apples, so they already reaches do the research probably work on 4 or 5 years. Their success rate I can point out still 60%. So they definitely are missing is either perception is wrong or the planner. Then even if they reach the apples, then maybe the gripper is too sleepy and they will miss the apples. That what happens because that's reality. Yeah.
Okay, thank you.
Another question.
Yeah.
When it comes to other fruits, like I know you've focused on apples, but do you think it would generalize well to most fruits that grow on trees? Like would it pick oranges and pears and whatnot just as well, or are there other considerations that would have to be adapted for?
Yeah, I can give short answers. Uh, the good strategy for picking any trees is shaking the tree. I can honestly tell you that. Then you talk about okay, you can share the tree. Yeah, you can share apple, especially cherry. They can shake the cherry tree, but you can. I mean, it's not a really good idea, for example, to develop this robot just do one-to-one picking, right? Because you think it is unnecessary. But the truth it is, some apple tree, only two apple trees you can shaking is the apple is easily to detach on the branches. So most apple trees, you're shaking the apple trees, the apple will not come down. And also that another interesting that not the apple is not a mutual, get a mutual all the apple at the same time. So for example, if a tree, right? So it's still 20%, it's not ready yet, and you should all shake the tree, they're all gone. So this is the reason that I prefer shaking the tree is the best solutions. But we are talking about is basically we talk about is called position act. It's basically way to do one-to-one. So this is for apple orange. Maybe I hope I guess orange maybe you can other approach can not do one-to-one. And but if you come to very small scales like a berry, strawberry, blueberry, that is a different scenario. Yeah, so because that again that they don't have like a modern tree apple tree here is two-dimensional. They have the branches somehow is like a blueberries, this inside branches. I do see some work. People will do the soft robot to develop the soft manipulator, very tiny one, to picking up the blueberry probably just once per 10 seconds. I'm not sure that's very practicable, but for research, yeah, it is. But we get a grant from USDA and NIFA. So the panel here, some panel members actually from industry and growers, and they really want to see any practical stuff. It's not just a research like NSF. So
any other questions? I guess one last comment is or question: how much marketable opportunity there is in this kind of activities? I understand there is no such a robotic solution right now. So is there an opportunity there to take this to the market and create a startup or things of that sort?
yeah, you ask good questions because we always have this conversation with growers. And what we're missing, honestly, is basically we don't have any marketing peoples here. So we tell the growers, so for science, we talk about, okay, we run the robot go fast as possible and pick as many as possible. But from the marketing point, doesn't make sense that the robot should pick all the apples.
Hmm.
So the grower said, okay, even I just pick 10% apples in 20 days, I'm still getting the best value. So they definitely behind, they have some marketing analysis behind that, how many robots need and what's the budget for the robot, what's the budget for label is what make the best profit. So I don't see for their conversation, it doesn't make sense. Everything needed to be done by the robot. So that's for the thing. But who knows? Maybe the robot will become much cheaper and much faster. Maybe they really pay that. And another thing we talked the commercialization part. We already talked to the IP office or the office commercialization here. So again, the grower doesn't have money to buy the robot, and we are thinking listing of options. So for example, here, if we can pick it 10,000 apples, I will list in the robot and how much you pay. So something like that. We really don't want so the grower to buy the machine, maybe just let leasing the machine to just like hire a label to do the job. So again, yeah, it's I feel it's more marketing side people are to do the analysis to guide our technology that what's the best parameters. It makes sense. Yeah.
Okay. Anybody else? All right. Well, thank you very much. Very, very insightful.
Right. Thank you very much.
And next time you come to this Bay Area, let us know.
Yeah.
Well,
Well, right. Thank you, everyone. Thank you, everyone.
Bye-bye.
Bye.
Getting connected with Martinelli's. The Martinelli portraits are down in Watsonville.